Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems, and in today's module we learn what memory management is. We will have an introduction to memory management and discuss about different issues related to memory management. So, the learning objectives for today's class are we will learn about the background related to memory management, and we learn what swapping is and different issues related to swapping, and we learn what contiguous allocation is with respect to memory management. So, we learned about a multi-program system in an earlier class where multiple programs can be placed in the main memory, or you can have multiple programs which are active simultaneously at the same time. And when a particular process is using the CPU, or when a process is under execution, then that process should be placed in the main memory, should be brought into the main memory, and it should be kept in the main memory. And to increase the system performance, you can keep many processes in the main memory. If the main memory is large enough to accommodate more number of processes, then many processes can be kept in the main memory, and the main memory space will be shared by the different processes that are placed. And how is this main memory space managed, and how is it shared between the different processes that are available? That is called actually memory management. So, the way in which the main memory is managed and it is being allocated for different processes. So, what is this memory? This memory is a large array of words and bytes, and the CPU will fetch the instructions to execute from the main memory based on the value of the program counter. So, the program counter will have the address of the next instruction to be executed, and looking at that instruction should be taken from the memory. And this instruction which is taken from the memory is decoded, and the operands that are needed for the execution of that particular instruction also have to be fetched from the main memory. So, once the operands are fetched from the main memory, the instruction can be executed, and the resultant of the instruction will be stored back into the main memory. So, this is what will happen during any instruction cycle. So, fetching instructions which should be present in the main memory, and the operands for the instruction, for the execution of the instruction, should also be taken from the main memory, and the results should be put back to the main memory. And now you have many processes and that are kept in the disk, that are waiting to be brought into the main memory so that it could be run. So, any process, as I told you, have to be present in the main memory to be executed, and it is not possible to place all the processes in the main memory at the same time, because your main memory space is not very large, as large to accommodate all the active processes. So, only the processes that can be accommodated will be kept in the main memory. The remaining processes will be kept in a backing store or in the disk, and these processes that are waiting in the backing store or in the disk are kept in something called an input queue. And one of the processes that are present in the input queue is selected and it is loaded into the main memory. And this process, after execution, after termination, then the can be removed from the main memory, and the space that is being allocated to this process can be freed. So, when you are looking at any user program, they go through a number of steps before they are run, and the addresses in the source program, they are generally represented in terms of symbols or in symbolic form. So, you have a program, you write a program, and this program will be in some executable file format, and that has to be converted into process where it has been put into the main memory. So, when any user writes a program, the symbols that has different variables will be in symbolic form. So, addresses also will be in symbolic form. And now the compiler will compile this program, and these symbolic form addresses will be now converted into relocatable addresses. Say for example, if you have a process, then any address will be from say 0 to some maximum for the particular process, and any address, say count, which is told in symbolic form in the source program, will be converted into some number saying that this corresponds to an address, say which is 15 bytes from the beginning of this module. So, the first address for that particular process will be 0. From then thereon it will be incremented and it will go to some maximum value for that particular process. And then the compiler will compile it into some relative address form, relative number form, and when this process is now loaded into the main memory, then some absolute addresses will be given to that particular variables or particular addresses. So, you have symbol form addresses initially in the program, and the compiler will compile and it will convert into some relocatable form, and then when it is actually loaded into the main memory, you have absolute addresses. So, address binding of instructions and data to specific main memory addresses can happen at 3 different stages. It can either happen in compile time, or it can be in loading time, or it can be in linking time. What is this compile time, loading time and linking time? Say if the memory location is known a priori, that is, if we know that this particular program after compilation, after forming a process, if it will be loaded to this particular location in the main memory, if that is known beforehand, then in that case the absolute addresses can be given even during the compile time. And the problem here is that if the starting location is changing, then you will have to recompile the program, so that it can be placed in the appropriate location. The next is to bind the addresses, or that is knowing the exact addresses where it will be placed in the main memory, can happen during the loading time. So, in this loading time, if it is done in loading time, it is not the addresses are not known in compile time, but the binding, the address mapping can be done during the load time. Or the third case is you can bind the addresses during execution time. So, it is not the address binding is not done during compilation or during loading, it is dynamically done while it is getting executed. If execution time binding is allowed, then the process can be moved even during its execution from one place to another in the main memory, because the binding can happen even during runtime. But for this we need hardware support for having the different address maps, and this is the one that is being used by most of the general purpose operating systems. So, now we need to know about 2 different terms. One is called the logical address and the other is the physical address. I told you that whenever a program is compiled and you generate relocatable addresses, which goes from 0 to some maximum value for that particular process. So, similarly each and every process will have their own 0 to max values, and now these program will be put onto the main memory on specific memory locations. So, this addresses, that is 0 to max for this process, will be mapped onto some physical memory location. Now, this 0 to max address is actually called the logical address, and where it is actually placed in the main memory is called the physical address, the actual physical location where that program or process is placed in the main memory. So, this logical address is the address that is generated by the CPU, and this is also called the virtual address, but the physical address is the address that is actually seen by the memory unit, where it is exactly placed in the main memory. and the logical and physical addresses are the same in compile time and load time address binding schemes. So, if you are binding in compile time and or if you are binding in loading time, then the logical address and the physical address are going to be the same. But if you are binding during the address binding during execution time, then logical address is different and the physical address is different. And now the set of all logical addresses generated by one particular program is termed logical address space. Very similarly, the set of all physical addresses that correspond to the logical addresses are called the physical address space. So, we need to understand that this logical address is some address that is relative to that particular process, and the physical address is the exact location where that process is placed in the main memory. So, now there should be some hardware device that will map the logical address to the physical address. So, if the logical address and the physical address are different, then there should be some conversion that is being done from this relative address that is related to that process, which is the logical address, to the physical address where it is exactly placed in the main memory. So, this is done by a memory management unit, and there are many schemes that are available for doing this memory management like the paging, segmentation and paged segmentation. So, in a simple memory management unit scheme, we will see how the mapping from the logical address to the physical address is done. Here a relocation register is maintained, and that relocation register will have the starting address of this process where it is placed in the main memory, and that address is added to every logical address that is being generated by the CPU, and that will give the exact physical address. So, the user program need not have to worry about the actual physical address, the real physical addresses where the process is exactly placed in the main memory. The user process just only have to know the logical address that is related to that particular program, and the memory mapping hardware will convert the logical addresses to physical address. So, here we will see this basic simple memory management unit mechanism where you have the logical address generated by the CPU. The CPU generates a logical address 346. This relocation register has got a value of 14,000, which is the initial starting address where this process is placed in the main memory. And so, the physical address is got by adding the relocation register, that is the base value, to this logical address that is generated by the CPU. So, I get 14,346 as the actual physical address where it is present in the main memory. So, this 346 is something which is related to that particular process. So, that is the 346th address in this particular process, and the process is placed where in main memory, it is starting from 14,000. So, this 346 in that process should correspond to 14,000 plus 346. So, that should be 14,346. So, this is a simple mechanism where the process is placed exactly in main memory starting from some particular location, and if you know the starting location, you can get the exact address for any logical address that is generated. So, logical addresses range from 0 to some max value, but the physical addresses range from R plus 0 to plus R plus max. That is, R is the relocation register value where you store the starting address from where that particular process is being stored. So, the user here, as I told you, need not know about where exactly the process is placed in memory. So, the user just thinks that the process runs in locations from 0 to max, and user will just supply the logical addresses. The logical addresses are converted to physical addresses before they are used. And now we have something called dynamic loading. In dynamic loading, what is done is that the routine, a function within the program, is not loaded until that particular function is called. So, a program or process can have a number of routines, a number of functions, and all these functions are kept on a disk in a relocatable loading format. And only the main program is loaded into the main memory, and whenever a routine or a function is called, the calling routine or the calling function will check if the called routine is already loaded into the main memory. If it is loaded into the main memory, then it can make use of that from the main memory itself. If not, it should be brought in from the secondary storage device into the main memory. So, the relocatable linking loader is called by this calling routine, and that will load the routine, the required routine or the required function into the main memory. So, what the loader, after loading the program, it will update the program's address table, and the control will be passed to the newly loaded routine. And the advantage of this kind of dynamic loading is that it has got better memory space utilization. How better memory space utilization? You do not load the full program into the main memory when that main process is taken for execution. Only the routines which are needed need to be loaded into the main memory. The other routines can be kept in the secondary storage device, and they can be loaded only if they are needed. Say for example, you can have some error routines which may not be used at all. So, those routines will not be called at all. Only if certain kinds of errors happen, those routines will be called, else those routines will not be called at all. So, no point in keeping all those routines in the main memory or load all those routines into the main memory. Only if such an error happens, those routines will be used, and only then they need to be loaded into the main memory. So, because of this, we save space, memory space. And for this dynamic loading, we do not need any special support from the operating system, and the users should design their program in such a way that it is modular, and you can have separate routines. They can design their program such that different routines are being designed, and the OS doesn't have to provide specific support. And for implementing the dynamic loading, the OS may provide library routines. And then we have dynamic linking. So, what is this dynamic linking? The linking of library routines, they are postponed till execution time. Say for each library routine reference that is made within the program, what is done is only a stub is included in the executable image. The actual code of the library routine is not included during compilation or when you get the executable image. And the stub is nothing but it is a small piece of code which will tell you the address of the library routine, where it is present in a memory and so on. So, it is used to locate the appropriate memory resident library routine, and when the small stub is executed, it will replace itself with the address of the routine and it will execute that routine. So, dynamic linking, because of dynamic linking, we do not have to include the code of the libraries when it is when the executable is formed. It is enough to bring in the library routines only when they are needed. Now, we move on to learn what is meant by swapping. As I told you earlier, a process needs to be present in the main memory for it to be executed, and all the processes cannot be kept into the main memory at a particular time. And we also have seen that a process will not make use of the CPU always continuously. A process can have CPU bursts followed by IO bursts, etc. and so on, and the process may not use the CPU continuously. So, any process that is using the CPU alone has to be kept in the main memory. So, processes which are not using the CPU can be moved to the backing store or can be moved to the disk, and then later they can be brought back into the main memory for execution when they are continuing the execution later. So what is this backing store? Backing store is nothing but it's a fast disk which is very large and it is large enough to accommodate all the memory images of process of all the users. And suppose if you are using a round robin scheduling algorithm, you can see you know that a time slice is allotted to each process. So there can be many processes that are active, and only some amount of time will be given to the given to a particular process. And after its time slice gets over, the process will be removed from the CPU and some other process will be given the CPU. And now say if there are 10 processes who are using this time quanta, and all the 10 processes may not be able to be kept in the main memory. We may not be able to keep all the 10 processes in the main memory. So only the process that is currently using the CPU or whose current time slice is getting executed need to be kept in the main memory. The remaining processes, if there is space in the main memory, you can keep them in the main memory. If there is no space in the main memory, the process whose time slice got over and if there is no enough space, they can be moved to the swapping space. And now say you need to take another process which needs to be given the CPU next, and if that process is not present in the main memory also, then in that case also you can bring the required process into the main memory by moving out some other process which is not going to use the CPU. And suppose if you are using priority based scheduling. In priority based scheduling, say a high priority process is coming in, then in that case a low priority process is moved out and the high priority process can be brought in. If there is no space for the high priority process in the main memory, then the low priority process which is using the main memory space can be moved to the swapping device and the required process can be brought in. This is also called as roll out and roll in. And now when you are looking at this swapping, a major part of the swap time is actually transfer time. Transfer in the sense you are trying to move the memory contents from the main memory to the secondary storage device and secondary storage to the main memory and so on. So this transfer time is again dependent or directly proportional to the amount of memory, how much amount of memory is swapped between the main memory and the secondary storage device. And modified versions of the swapping, they are found in many operating systems. Say for example Unix, Linux, Windows, they all use variants or different variations of swapping. So this figure just shows how swapping happens. You have the main memory where the main memory has the operating system, and you also have the user space where the user defined programs and processes can be placed in. And user processes from here have to be removed and can be brought to the backing store if some other process has to be brought in. So if P2 has to be brought into the main memory, and say if P2 needs to get the CPU next, then P1 can be removed out or swapped out and P2 can be brought in. And now we will see how memory is allocated for process. I just told you that many processes can be kept in the main memory. You can have a number of processes placed in the main memory, but where do you place all these processes in the main memory? Do they have some specific places where they can be placed, or can you place anywhere in the main memory and so on? Generally, as I told you, your main memory has got two partitions. One is you have low memory and the other is the high memory. Usually the operating system is placed in low memory and the interrupt vector is also placed in the low memory. And the high memory is used for user process and the user defined process can be placed in the high memory. And as I told you, like processes that are waiting in the input queue should be brought into the main memory, and each process can be placed in a single contiguous section of memory. So that is called contiguous memory allocation. That is, a process that is brought from the input queue into the main memory is placed contiguously in the main memory. They are not split into pieces and but they are kept contiguously in the main memory. This is one way of memory allocation. And even in contiguous memory allocation, you can have single partition allocation or you can have multiple partition allocation. In single partition allocation, the whole memory is looked at as a single big partition, and use a basic scheme like the relocation register scheme, where you protect one user process from the other process and so on. So, you bring in the process, put it into the main memory, and you remember the starting address from where this particular process is kept in the main memory, and that starting address is placed in the relocation register. And you also have a limit register which gives the length or the range of addresses for that particular process. And when you have this relocation register content and the limit register content, then any address generated can be checked if they are proper, just like how you look at this diagram. So, any address that is generated for a particular process is checked with the limit register value for that process. That is, you check if the address generated is less than the limit register value. If it is less than limit register value, then you add it with the relocation register to get the actual physical address. So, any address that is generated for this particular process is checked if it is within its limits only, and only if it is within its limits, then the actual addressing is being done, or you locate to that particular memory. It is also possible to have multiple partitions. In multiple partitions, it is also possible to have fixed size partitions as well as dynamic partitions. In fixed size partitions, what is done is the main memory is divided into several fixed size partitions, and whenever a partition is free, a process is selected from the input queue and is loaded into the free partition. When the process is no longer going to use that particular partition, then that space can be freed and can be used for other processes. The other case is to have, even in multiple partition, is to have dynamic size partitions. That is, the whole block of available memory is looked at as a single big whole, and whenever a process is arrived, it is allocated a memory from the whole which is large enough to accommodate it. In due course of time, what will happen is that you will have holes here and there, because varied size processes will come in and go. When a process terminates, the space is freed and it is added to the set of holes. So, at some point in time, you will have a number of holes, and any process that comes in will be put into any of these holes, which is that is basically put into a hole which is large enough to accommodate that particular process. And for implementing this, the operating system should have information about the allocated partitions and the free partitions. So, you have the list of holes, and you know whichever holes are allocated, whichever holes are free. So, whenever any process comes in, it is put into the hole which is free and it is large enough to accommodate that process. So, here look at this example, you have the operating system in the main memory, process 5, process 8 and process 2 are present in the main memory, and then process 8 goes off, it is removed, and you have one large hole here. And then process 9 comes in, that is put into this hole, and then you have the remaining place as the hole. And then another process 10 comes in, that is put into the hole that is available, and then you have some remaining space which is free. So, this is called contiguous allocation, where you have varied size partitions and the allocation is done dynamically. And now we have a problem, that is you have a request of size n and you have a list of free holes. Into which of these free holes are you going to place this size n or n sized process? We have three ways in which you can place. One is called first fit. In first fit, the first hole is allocated, or the first hole that is big enough to accommodate this process is allocated. So, what you need to do, you need to either start searching from the beginning to find a hole that is large enough to accommodate this process, or you will have to start from where you had finished the previous search and then try to accommodate this process. And the next mechanism is to have best fit. In best fit, what is done is you allocate the smallest hole that is large enough to accommodate the process. Again, you need to search the entire list, but if the list is ordered by size, then you can search based on that, and this will produce the smallest leftover hole. And the next way is to go for worst fit, where you allocate the largest hole that again is large enough to accommodate the process. And if you look at this kind of first fit, worst fit and best fit allocation algorithms, we see that they suffer from external fragmentation. So, what is external fragmentation? You have a list of holes and you put process into the hole, remove them out, etc. and so on. At some point in time, you will have holes here and there. Say you will have space enough that is large enough to accommodate a process. Say 10 bytes of space may be available, but may not be available contiguously. It will be present say as some 5 byte, 2 byte, and then again say some 3 byte and so on in 3 different places. So, if you are trying to bring in a process of 10 byte of size, you cannot accommodate the process. So, this is called external fragmentation, and how can this be reduced? It can be reduced by means of compaction. So, what is compaction? You shuffle all the memory contents to place all the free memory together into one large block. And this compaction is not possible only if relocation is static and it is done, the relocation is done at assembly time, or the address mapping is done at assembly time or load time, but it is possible only if relocation is dynamic and it is done only at execution time. So, summary of what we have learned today. We saw that a process should be kept in main memory during its execution. We saw that the addresses that are generated by the CPU with respect to that program are called logical addresses, and the addresses where they are exactly placed in the main memory are called physical addresses. And it is possible to have dynamic loading and linking. Dynamically you can load a routine only when needed, and dynamically you can link your library routines during execution time. And swapping of processes between the main memory and the backing store takes place because of lack of enough space in the main memory. And we also learnt about contiguous memory allocation, where the process is contiguously placed in the main memory. So, in contiguous memory allocation we learnt about fixed size partitions, we learnt about varied size partitions as well. References, acknowledgement. Thank you.